Let's create another toolbox, which will be our summary of equations for open thermodynamic systems. For open systems where we have a fluid flowing through the system, let's begin by writing continuity equations. Now, continuity equations have multiple assumptions. One is that the systems are operating at steady state. They have a single inlet and outlet. They have one-dimensional flow across the conduit that the fluid is flowing in. And in that case, our basic mass flow rate balance is that the mass flow rate at the inlet is equal to the mass flow rate at the exit, and we'll just call it m dot, the mass flow rate. We can determine what the volumetric flow rate is. The volumetric flow rate is just the area of the conduit in which the fluid flows times the velocity at the cross-section. That's also equal to the mass flow rate times its specific volume. Now, the remaining equations are just derived from the first two. We can say that the mass flow rate is the volumetric flow rate divided by its specific volume, and the volumetric flow rate is area times velocity. We can also write this as the mass flow rate is rho AV. Often rho is a more commonly used property than specific volume when you're in situations outside of thermodynamic analysis. We can also write an inlet-outlet ratio that AV over specific volume is a constant. So the area at state 1 times the velocity at state 1 divided by the specific volume of state 1 is equal to the area at state 2 times the velocity at state 2 divided by the specific volume at state 2. Now, we've seen this before, that the enthalpy change for gas, and this will be specific enthalpy, is just C sub P delta T, and that is for a gas. But when we're dealing with liquids or solids, we have a different equation. And we introduced this. It's very handy in many problems, that delta H during a process involving a liquid or a solid is C delta T plus V delta P. So that's the specific heat times the change in temperature plus the specific volume times the change in pressure. We introduced an energy balance for an open system. We said that d dt is 0 because it operates at steady state. And that's simply equal to Q dot minus W dot plus M dot times the change in enthalpy plus the change in kinetic energy plus the change in potential energy. And we applied this energy balance to various thermodynamic devices. The first two devices we looked at were nozzles and diffusers, which are used, nozzles speed up the velocity and diffusers slow down the velocity. That's their primary function. And if we ignore changes in potential energy and any heat transfer that may take place between the surroundings and the system, then our energy balance can be reduced to 0 is equal to H1 minus H2 plus V1 squared minus V2 squared over 2. Now, with turbines, if we ignore changes in kinetic and potential energy, which are usually small, and also if we ignore heat transfer between the turbine and the surroundings, we get a very simple energy balance, that the power output of a turbine is just the mass flow rate times H1 minus H2. Compressors, we get the same equation if we make the same assumptions. If there's no significant heat transfer or change in kinetic or potential energy, then the power requirement of the compressor is just the mass flow rate times H1 minus H2. Now, for pumps, there isn't much we can ignore, since pumps often increase velocity and increase potential energy. The only thing we may ignore typically in a pump system is the heat transfer between the system and the surroundings. And if we ignore that, we get that W dot is M dot times the change in enthalpy plus the change in kinetic energy plus the change in potential energy. Now, throttling devices are basically pressure dropping devices. But if we ignore heat transfer and changes in potential energy, and often we can ignore changes in kinetic energy, then we end up with a constant enthalpy device. So in many situations, the throttling process is just a constant enthalpy process. Now, if the velocity increase through the throttle valve is so great that it cannot be ignored, then we would have to include the kinetic energy term in our energy balance, and then the throttling device would no longer be a constant enthalpy device. Let's look at things like boilers and furnaces or evaporators or condensers. They're basically just a simple heat exchanger where we're heating or cooling a fluid flowing through them. And we can write the equation for heat transfer is Q dot is just the mass flow rate times the enthalpy at the exit minus the enthalpy at the inlet. Now, if we're dealing with an incompressible liquid instead of a gas, then we can write that the heat transfer rate is the mass flow rate times the specific heat of the fluid times T2 minus T1. Now, heat exchangers get a little more complicated, but if we look at the heat exchanger as a system, we draw our boundary around the entire heat exchanger encompassing both flows, the flow on both sides of the heat exchanger. We know that all of the energy entering the heat exchanger has to be equal to all of the energy leaving. So we can write this expression that the summation at the inlet of the mass flow rates at the inlet times their respective enthalpies is equal to the summation at the exit of all the mass flow rates at the exit times their respective enthalpies. And again, when we analyze the heat exchanger as an entire system, we can write this expression that the mass flow rate at state 3, which is the inlet to one side of the heat exchanger, divided by the mass flow rate at state 1, which is the inlet to the other side of the heat exchanger, is just H1 minus H2 over H4 minus H3. So if we know one flow rate and can determine all the enthalpy values, we can determine the other mass flow rate. Now, if we want to find the amount of heat transfer that transfers between the fluids inside the heat exchanger, we have to analyze the system differently. We have to just look at one side of the heat exchanger or the other. Here I'm looking at the side where we have flow coming in at 1 and exiting at 2. We can see that the heat transfer rate between the inlet 1 and the exit 2 for this heat exchanger is the mass flow rate at state 1 times H2 minus H1. We could have done this easily for the other side of the heat exchanger where we're looking at stage 3 and 4. We could have said that the heat transfer for the fluid between state 3 and 4 is just the mass flow rate at the inlet 3 times H4 minus H3.